Section 9.5 is the binomial theorem. So expansion of polynomials requires distribution and combining of like terms. So looking at the ones we have down here, like x plus y squared ends up being x plus y times x plus y. We got to go through and we got to distribute. Now sometimes, sadly, people refer to this as foiling. However, there is a process that we can do that can expedite this to speed things up using some patterns. And yeah, that's what we're going to look at right now. So recall that a binomial is a polynomial that has two terms. In this section, we're going to study a formula that provides a quick method of raising a binomial to a power. To begin, let's take a look at the expansion of x plus y to the nth power for several values of n, so several different x values, or sorry, exponents. So x plus y to the 0. Anything to the 0 is just 1. Doesn't matter what x and y are, x plus y to the 0 is always 1. X plus y to the first. Anything to the first is just x, or is just itself. So x plus y to the first is just itself. So it's just x plus y. X plus y squared. Remember, x plus y squared really means x plus y times x plus y. And we'd go through and we distribute. We end up with x squared. We end up with x times y. We end up with another x times y. And we end up with y squared. And then when we combine those together, those two like terms, we get that 2xy in the middle there. Now we could take that and multiply it by xy again, so it'd be like x plus y cubed, which would be x plus y times x plus y times x plus y. Well, we already did like two of those together, so it would just be like x plus y times what we just found in the previous one, x squared plus 2xy plus y squared. And then we can go through and distribute that again. And after we simplify all of that, we'd end up with what we see here, x cubed plus 3x squared plus 3x squared y plus 3xy squared plus y cubed. And we can keep going and going and going further and further down the line. So like x plus y to the fourth is ends up being x to the fourth plus 4x to the third y plus 6x squared y squared plus 4xy to the third plus y to the fourth. And finally on this one, x plus y to the fifth simplifies to be x to the fifth plus 5x to the fourth y plus 10x to the third y squared plus 10x squared y to the third plus 5x y to the fourth plus y to the fifth. You might already start to see a little bit of a pattern here. To help us identify this pattern a little bit better, we're going to take a look at good old Pascal's triangle. Now this is something you've probably seen before. If you look at the bottom of the page, you can probably read about how to find it. Remember, the outside numbers in Pascal's triangle are 1s, and every number in the next row is the sum of the numbers right above it. So for example, we get 1 plus 1 gives us that 2. So now to make our next line, we're going to follow that same pattern. So the outside number is 1. Then we're going to take these two numbers together and get 3. We're going to take these two numbers together and get 3. We also have a 1 on the outside. We're going to repeat the process as many times as we need. We got a 1, we got a 4. 3 plus 3 gives us 6. 3 plus 1 gives us 4. And we got a 1 on the outside. We go a couple more rows. 1, 5, 4 plus 6 is 10. 6 plus 4, also 10. 5, 1. And let's do another 1, 6, 15, 20, 15, 6, 1. And again, we can keep going for, well, literally forever if we have enough space. Now, just a quick reminder, just kind of summarizing what at the bottom here. The first and last numbers of each row are 1s. Every other number is formed by adding the two numbers immediately above it and directly above it. Pascal knows the numbers on this triangle are precisely the same numbers that are the coefficients of our binomial expansions, as follows in the next page. But before we get to that next page, I actually want to talk about one more thing. I'm going to give these rows names. So like the top row, I'm going to call it row number 0. That's going to become important in a little bit. The second row, the one below the row 0, we call row 1. And I would just keep going, row 2, row 3. And one way you can kind of help identify those row names is like with the second number in that. So like this one has, well, a 0. It has no extra numbers there. This second number is a 1. This second number is a 2. This second number is a 3. And so you can kind of identify it. And again, I'll come back to why these might be helpful in just a second. Let's flip over to the next page. So we've got the examples that we just did, goes even further than x to the fifth. Now we got x plus y to the fifth. Now we got x plus y to the sixth. You'll notice all of the coefficients, x plus y to the 0 just simplifies to 1, conveniently matches up with that 0th row, that top row of Pascal's triangle. x plus y to the first. The coefficients after you simplify it are 1 and 1. Again, they match up with the row 1 of Pascal's triangle. Then 1, 2, 1 matches up with row 2 of Pascal's triangle. For x plus y to the third, 1x to the third plus 3x squared y plus 3xy squared plus 1 y to the third. The pattern keeps on going. Every row, the coefficients are going to come from Pascal's triangle. You'll see this one, as I said, it goes to x plus y to the sixth and x plus y to the seventh. We did the row 6 on the previous one where we went 1, 6, 15, 20, 15, 6, 1. We could have gone to the 7th row and gotten 1, 7, 21, 35, 35, 21, 7, and 1. Now, using that information there, we're going to see if we can come up with the next row, the 8th row of Pascal's triangle. I also want you to keep in mind what this notation might remind you of. Something we'll talk a little bit again later. But for now, we're just going to use those as like the coefficients in row 8, position 0, position 1. So the first coefficient in row 8 is going to be, well, 1. The next one, we're going to do the 1 plus 7, giving us 8. And we're just going to kind of move down the line. 7 plus 21 gives us 28. 21 plus 35 gives us 54. 35 plus 35 gives us 70. Let's see, we're down to 35 and 21 here, so we're back to 54. And then we got another 28. Then we got an 8, and then we got a 1. You'll notice, in case you didn't notice this before, everything kind of repeats itself. There's always like a midline. So looking at this, like our midline would be kind of right here. Everything, it's like not quite a palindrome, but the numbers repeat themselves on both sides of the line. Some rows have a middle number that we can use. Now, for binomial expansions, we're going to use this pattern. I'm going to show you kind of a structure that you can use to help us out with this. So, x plus 1 to the third. What I'm going to suggest is we go to row 3 of Pascal's triangle, kind of following this pattern here. So I'm just going to write down those coefficients of 1, 3, 3, 1. And I'm going to leave them spaced out. Below that, what I'm going to have us do is kind of identify some patterns. Let me actually go back up to the top here. Looking at maybe, let's say, row 5. Looking at row 5. We got 1x to the 5th. You'll notice there's no y's there. The next one's got 5x to the 4th, y. The next one's got 5x to the 3rd, or sorry, 10x to the 3rd. I want to focus just on the x's. The x's go x to the 5th, x to the 4th, x to the 3rd, x to the 2, x. You could also call that x to the 1st. And this one doesn't have an x, but you could treat it like as an x to the 0 because that's just 1. So we're going to follow the same kind of pattern down here. So we're going to do the first term of x, we got x to the 3rd, x to the 2nd, x to the 1st, and x to the 0. Now going back up, I'm going to go to row 5 there again. The y's. There are no y's here. It's almost as if there's y to the 0 power. This is y to the 1st. We got y to the 2nd, y to the 3rd, y to the 4th. The y values the y exponents are getting larger. So we're going to do that same thing with the second term here. We're going to do 1 to the 0, 1 to the 1, 1 squared, 1 to the 3rd. Now this one's not super exciting because it's just the number 1, and 1 to any power is always 1. But what we can do now is take each of these columns. I'm going to kind of like label them off. You don't have to draw these lines there, but sometimes it's nice. What we're going to do is we're going to take each of these and, well, simplify it. So the first row, we got 1 times x to the 3rd times 1 to the 0. Well, 1 to the 0, just to clarify, is 1. So it's 1 times x to the 3rd times 1 gives us x to the 3rd. The next row, we got 3 times x squared times 1 to the 1st. Again, that's just 1. So 3 times x squared times 1 gives us 3x squared. Next up, we got 3 times x to the 1st times 1 squared. Well, again, that's just 1. So 3 times x times 1 gives us 3x. And the last one, we got 1x to the 0. Remember, anything to the 0 is 1, and then also 1 to the 3rd is 1 as well. So we got 1 times 1 times 1, so it just simplifies to be just 1. So x plus 1 to the 3rd is simplified as x to the 3rd plus 3x squared plus 3x plus 1. Now example 2 is very similar, but instead of x plus 1 to x plus 1 to the 3rd, we're dealing with x minus 1 to the 3rd. So we're going to use the same coefficients, the 1, 3, 3, 1. We're going to use that same x again. So we're going to do x to the 3rd, x squared, x to the 1st, and x to the 0. So we're going to take that first term, raise it to the highest exponent, in this case 3, and work our way down. Then we're going to take the second term, the negative 1, put that in parentheses and raise it to the 0. The second term we're going to take and count up. So we got negative 1 to the 0, negative 1 to the 1st, negative 1 squared, and negative 1 to the third. Now again, we're going to do the same thing, kind of going by each column. Let's clean up a little bit. First row, 1, 3, 3, 1, nothing clean up. I'm just going to cross off the exponent because x to the first is just x. X to the 0 is 1. The third row, negative 1 to the 0 is positive 1. Remember, anything to the 0 is 1. Negative 1 to the first, I'm just going to rewrite that as negative 1. Negative 1 squared, that's positive 1. And negative 1 to the third, simply put, is just, oops, sorry, not negative 3, but negative 1. So now working through this first column again, we got 1 times x to the third times 1. That's just nice, and x to the third. The second one, we got 3 times x squared times negative 1. That gives us negative 3x squared. The third column, 3 times x times 1. That just gives us 3x. And the final column, we got 1 times negative 1, which gives us negative 1. So do make sure that you're including including the negatives inside those parentheses where appropriate. On the next page, let's try out a couple more difficult ones. So on example 3, we got 2x minus 3 to the fourth power. That fourth power, we're going to have to go to row 4. So I'm going to flip back to Pascal's triangle. The numbers go 1, 4, 6, 4, 1. So let's jot those down. So our coefficients to start 1, 4, 6, 4, 1, and again, give it a little bit of space. Next up, we're going to take that first term, the 2x, and we're going to start with the highest exponent. So we're going to go 2x to the fourth. Put that in parentheses because we're raising the whole thing to the fourth, not just the x. So we got 2x to the third next, then 2x squared, 2x to the first, and then finally 2x to the 0. Then we're going to take that minus 3, do the same thing, but instead of counting with or starting with the highest exponent, we're going to start with 0 and work our way up. So negative 3 to the 0, negative 3 to the first, negative 3 squared, negative 3 to the fourth, and sorry, not to the fourth, I got ahead of myself. Negative 3 to the third, and negative 3 to the fourth. Now we're going to have to clean this up a little bit. 2x to the 2x, the whole thing to the fourth, means we're going to take 2 raised to the fourth and x raised to the fourth. 2 to the fourth is 16, so we got 16x to the fourth. 2x to the third, well, 2 to the third is 8, and then we got x to the third. 2x squared is going to give us 4x squared. 2x to the first, we can just pretend that exponent doesn't exist, so it's just 2x. And then 2x to the 0, and remember, anything to the 0 is just 1. Bottom row, negative 3 to the 0, 1. Negative 3 to the first is, well, just negative 3. Negative 3 squared is positive 9. Negative 3 to the third is going to be negative 27. Negative 3 to the fourth, that's going to be a positive 81. So let's go through and clean up each column. First column, we got 1 times 16x to the fourth times 1. That gives us 16x to the fourth. The next column, we got 4 times 8x to the third times negative 3. Well, focusing just on the values, we got 4 times 8 giving us 32 times negative 3, which gives us negative 96. Oops, sorry, 96. And then we also have the x to the third. Our next column, we got 6 times 4x squared times 9. Well, 6 times 4 is 24, times 9 is 216. So we got a positive 216, and don't forget about that x squared, that's part of it. Next up, we got 4 times 2 times negative 27. That also, not so coincidentally, is negative 216. And then we just have x to the first there. The final one, not so painful. 1 times 81 just gives us 81. Now, folks, I know that in itself isn't the quickest of processes, but that is substantially quicker than having to do 2x minus 3 times 2x minus 3, and then take that and multiply that by 2x minus 3 and distribute that, and then take that and multiply that by 2x minus 3, and having to go through and distribute. You're going to be distributing for quite some time. So even though this is a little tedious and it's a little detail-oriented, it's still way faster than it could be. Let's try one more. We got x minus 2y to the fifth power. So, again, going to the coefficients we found in the fifth row. So I drew a straight line in there. Let me get rid of that. So, the fifth row, 1, 5, 10, 10, 5, 1. Let me write those down on that page. So, again, 1, 5, 10, 10, 5, 1. I'm leaving myself a little bit of space in between those numbers so that way we can work it. Starting with the first term, x. Again, we're going to take the first term and raise it to the highest exponent and then kind of work our way down. X to the fourth, x to the third, x squared, x to the first, and then x to the 0. Then we're going to take the negative 2x and then kind of work our way up. We got negative 2x to the 0, negative 2x to the first, negative 2, oops, sorry, goodness gracious, I'm writing x and it's y. So we got negative 2y to the 0, negative 2y to the first, negative 2y to the second, negative 2y to the third, negative 2y to the fourth, and finally negative 2y to the fifth. Now, cleaning up some of this, the first row, nothing to clean up there. The second row, the only thing we can really clean up is, let's just get rid of that exponent so it doesn't confuse us. And then x to the 0 is 1. Bottom row, negative 2y to the 0 is just negative, or sorry, that's just 1. Negative 2y to the first is just negative 2y, so I'm just going to cross off the parentheses. Negative 2y squared, that's positive 4y squared. Negative 2y cubed, well, negative 2 cubed is negative 8, and then we have the y cubed. Negative 2y to the fourth is going to be positive 16y to the fourth. And finally, negative 2y to the fifth. Negative 2 to the fifth is negative 32y to the fifth. And again, we're going to go through each column. So kind of going through the first column, we got 1 times x to the fifth times 1. That gives us just x to the fifth. Let me make a line here. 5 times x to the fourth times negative 2y. So 5 times negative 2 gives us negative 10. Then we have x to the fourth and y involved there. Next up, we have 10 times x to the third times 4y squared. Well, 10 times 4, that's 40. We also have an x to the third and a y squared. Next up, we got 10x squared negative 8y to the third. Well, 10 times negative 8, that gives us negative 80. Then we have x to the second, y to the third. Next up, we got 5 times x times 16y to the fourth. 5 times 16 is 80, so we got plus 80x, and then, sorry, y to the fourth. And finally, in that last column, we got 1 times 1, I can do that in my head, times negative 32y to the fifth, so we end up with just negative 32y to the fifth. And that, my friends, is the binomial expansion.